Hey everybody, thanks for coming here. My name is Massi. I'm a software engineer at Datadog. I used to do mostly C++ and Python. Nowadays is Python and Go. I joined Datadog almost 2 years ago, and I work in the agent integrations team. Datadog is a software as a service providing infrastructure, application, and recently logs monitoring. The most common use case is you basically run our agent on one of your boxes, and the agent collects and sends data over our backend. This data is processed, and we can provide you with insightful dashboards, visualization, and also alerting. Just to give you a sense of the throughput we handle, we process almost trillions of data points each day. This is a subset of the services, databases, softwares that we can collect metrics from. And we have almost 200 of this, and for 75 of these integrations, they are actually implemented in Python. There is some Python code collecting metrics. Let's see how it works. So the agent is a Python open source project, and it acts as a daemon. So it runs on your machine, and every 15 seconds executes the checks, and collects metrics. So users can configure which kind of checks they want to run, can enable and disable checks. So let's say you want to run the Postgres check and the Redis check. When the agent starts, it loads the Python modules corresponding to the checks, and every 15 seconds goes through the Postgres check, collects metrics, send metrics, Redis check, collects metrics, send metrics, and so on. This is how the average check looks like. So it's basically a Python class implementing some sort of interface, pass me the term. Specifically, it has to implement the check method. And this is the method that is called by the agent every 15 seconds. What you usually do in the check body, you interact with the services you are monitoring, you collect metrics, the events, do some processing maybe, some logic, and then you can use the Python API exposed by the base class to send metrics upstream. So the agent is a pretty good piece of software, you have to say, but it's 5 years old. So recently, the number of issues we had that required a complete rewrite of the software started to pile up. So we decided to just start from scratch with the next generation agent. We had two requirements, though. First of all, the new agent had to be smaller in footprint, faster in collecting and sending metrics. And another strong requirement was whatever language you pick, just keep Python around. This is because we have, as I said before, almost 75 checks implemented in Python that we don't really want to port to Go. Also because Python is the right language for most of them. Also, since when you run the agent, you can actually run any arbitrary piece of Python code. We have an undetermined number of custom checks that our customers might want to keep using. And last but not least, we cannot just port the checks to Go and build everything in a single executable and say whenever you need to update, let's say the Postgres check, one line of code change, you have to recompile the entire agent and redistribute the entire agent. We wanted to keep separated the core from the checks. And we decided to implement the agent in Go because the first requirement was pretty easy to achieve. And the second one, let's have a look at what we did. As you might already know, Python can be embedded. This means from your Go application, but could be Rust, C++. You can actually load an interpreter in memory and ask the interpreter to run Python code at will. CPython provides a pretty good C API to allow embedding. And Go as a mechanism, let's say, a mechanism maybe, a set of tools that are called CGO that enables the creation of Go packages that can actually call C code. And since CPython is in C, well, bingo. Let's have a quick look at the code. How many of you are familiar with Go? Whoa, nice. Gotham Go is like Midtown West. So let's say we have this piece of Python code, just a function in a foo module, and we want to run this Python code from Go. So let's write a super small main function. So what is cool here is that even if you don't know Go and you don't know CGo, it doesn't matter because we are using this open source project called GoPython that basically hides all the details that you need to know about C programming. So what you get using this package is that you can map one-one the C API with Go code. So this is our application entry point. We initialize the interpreter. So we say Python start. Then we import the module, and we can pass the string of the module we want to import, in this case, foo. Some error checking, the module might not be there, stuff like that. Once we have the Python module in memory, we can get the function from the module. So we get the symbol by name. From the foo module, we get the hello function. Another bit of error checking, and finally, we can call the function. So you may notice the function is not taking any argument, but you know that under the hood, we actually need to pass the tuple containing the args and the dictionary containing the keywords. In this case, both are empty, but I need to call the function passing args and keyword args anyways. Finally, when we don't need the Python anymore, we can call finalize. So what you have to do to build the executable, even if we are using CGo, we basically don't care because the Go toolchain is taking care of all the implementation details. And we can run the executable and get segmentation fault. I need to specify where is the Python path. Otherwise, Python cannot really find the module. So here it is, a Go binary executing Python code. What is cool, we can change the Python code here. And without recompiling the binary, Go will just pick up the new version of the module, and that's it. Is that easy? Of course it's not. So as you may already know, we have to deal with the GIL. The GIL stands for Global Interpreter Lock, and of course CPython embeds the GIL. Basically, the GIL is a global mutex that prevents multiple threads to run Python bytecode at the same time. So even if you have a Python multi-threaded application running on a multi-core architecture, there's no way you are going to use more than one CPU at a time. Since we are embedding CPython, we are also embedding the GIL. And the problem is, if the Go binary is running some Python code, and this Python code starts and stops threads, that's fine. The GIL will take care of that. But what happens if you are running the interpreter from different threads from Go? At that point, the GIL doesn't know anything, doesn't know what's going on. So let's see what happens if we run Python from different threads. How many of you are familiar with the concept of Go routine? Okay, not that many. So think about the Go routine as a tasklet in this stackless Python world. So a Go routine is some sort of lightweight thread. The only difference is in Python, you usually, when you use greenlets or tasklets, the greenlets run on the same thread. In Go, a Go routine can run on multiple threads. So you might have 4 Go routines running on 4 different threads, or 4 Go routines running on the same thread, as you would do with greenlets. Let's quickly see another example. So I'm going to change a little bit the Python code because I actually need the CPU to do something to expose the issue. In this case, it's just a for loop, like adding an integer to number. Pretty easy. The Go code is like this. I hope it will be clear even if you're not familiar with Go. But basically now, as before, we import the module, we import the function. But now we call the function from 2 different Go routines. So I have a loop of 2. First iteration, I start a Go routine calling Python. Second iteration, I start another Go routine calling Python. Since the Python is doing something, we will have, like for some time, we will have both the Python modules run at the same time. So let's see what happens here. Yeah. So I will save you the stack trace, but basically we segfaulted. So what happened here is that we might expose any number of race conditions and problems because basically Python is convinced that is running only on 1 thread, but we are doing slightly different things. So how do we fix this? Basically, since the GIL doesn't know that Python is running on different threads, we need to take control. We have to manually handle the GIL. Specifically, from here, we can tell Python, we are taking control. Turn the autopilot off. I will take care of locking the GIL by myself. And at the end, of course, we will give Python back the control. And that's one thing. Between here and here, we are on our own. We need to take care of the lock by ourselves. So what we need to do here, before calling in Python, we need to acquire the GIL. And when we are done, so we know from this point down, we don't need to call Python anymore, we release the GIL. So other pieces of Go code running Python will be able to run. Let's try to compile again and to run. This time, the 2 Go routines were able to finish without any issue. So now here is the tricky part. As I said before, if you have greenlets, they are supposed to run on the same thread all the times. With Go, this is not true. You might have multiple Go routines running on different threads, but could be worse. You might have a Go routine that starts on a thread. Let's say you have 4 threads, 1, 2, 3, 4. A Go routine starting running on thread 1. At some point, the Go runtime says, okay, you can go to sleep because I need to do other things. And the Go routine is paused. Then it's resumed. At a later time, it's resumed, but not on thread 1, on thread 3, maybe. So what happens if you lock the GIL on thread 1, go to sleep, resume, and unlock the GIL on thread 3? Let's see another example. We're going to use the same Python code here, so that's fine. And hopefully we will be able to expose the issue. I need to cheat a bit. To force the Go runtime to pause my Go routine, I need to do a time sleep. So here, it's the same code as before. We are on 2 Go routines invoking Python. The only difference is I call Python, I sleep, I call Python again. As you can see, we have the GIL handling in place. So I don't know if it's better like, okay. I hope you can follow the code. But basically, the GIL is handled like we did before. The only difference here is that this go routine might be paused by the runtime during this sleep. Let's build the binary. Okay, another cool segmentation fault. That's not actually a seg fault. This is more Python aborting the execution. And yeah, I cannot really show you the error, but basically Python is saying, hey, you locked the GIL from, actually what Python says exactly is you are trying to unlock the GIL on a thread, but the GIL was not locked. So what happens here is that you lock the GIL from thread 1 here, then you run some Python, you go to sleep, the go routine is resumed on a different thread, that different thread doesn't have any GIL locking in place, and Python just aborts. The only solution I found to this is to basically beg the Go runtime, please, if you're going to post this Go routine, when you resume it, please resume it on the same thread as before. This, let's see if it works. It should. So this has some performance implications, of course, but the point is the agent, it's not a real-time critical application. We can afford, it works. We can afford to spend some time not being so efficient because of this, because what we gain is running Python, which is cool. Another nice thing you can do when you embed Python, you can do the other way around. You can extend Python. So instead of just calling Python code from Go, you can call Go code from Python. And you need to write a little bit of C to implement this. We're going to see a quick example. But it's very, very easy to do. This would be the function in Go that you want to call from Python. So easy. This is the C code you need. What we are doing here, basically, we are going to create my module in memory. It's a fully functional module, but it's in memory. And we are going to manually add to this module functions, classes, whatever. In this case, we are going to map the Go function we have seen before with the name within that module. So the Go function will be known in the Python world as my_func. Finally, this is the Python code you can run. So when you do my module, you are accessing a module that only lives in memory. And when you call my_func, you are actually calling a Go function. Of course, this only works if you run this Python within the embedded interpreter. If you run this code in a random Python interpreter, my module doesn't exist. So what I learned from this experience, embedding Python is cool because you can keep writing idiomatic Go code without bothering that you are actually also using Python code. The overhead is close to 0. It doesn't matter. It's like having the same code in memory. And you can also extend Python, which is a very powerful tool. For example, in our agent, we parse the configuration file in Go, and instead of parsing again the configuration file in each check, we expose the data structure containing the configuration bits to Python through a module. What went not so good? The GIL prevents Python parallel execution, and this was expected. I mean, we already knew that we cannot run Python in parallel. The problem is, and I didn't see this coming, that the way the Go scheduler works doesn't really play really well with the GIL. And also I tried to run multiple interpreters because, You have a Python in memory, why not 2 or 3? The problem is, if you are on the same binary, the 3 Python interpreter are going to share the GIL, so no way. So what worked, kind of, we have to carry on some C code. So you have Go code, Python code, and also C code. But it's not that bad, because it depends on the use case. We don't have that much C code. And yeah, you will likely also need to carry on some Python code to provide like base classes for your Python code that is going to run in the embedding interpreter. What we have right now, last week we released the first beta of the new agent that embeds Python 2.7.13. Don't ask me why it's not Python 3. It runs on Linux, Mac, and Windows. And now, instead of having the checks running like one after the other, the architecture is now completely asynchronous. So the checks are running at the same time, but not in parallel, of course. Even if we ported few core checks to Go, so what happens, really what happens is that you might have a Go check running in parallel with a Python check. Of course, no two Python checks running at the same time, unfortunately. And we open sourced the project, so if you are curious, please stop by and start the repo. And if you like this kind of stuff, we are hiring, so please reach out. Thanks. I don't know if I have time for questions. Any question? Yes.
Sorry, so you said you're still running the Python checks in parallel, or is it not?
We can. I mean, concurrently, but not in parallel.
Okay.
Yeah. So you feel like they are in parallel, but
Right. But you basically run this. Sorry.
yeah, just yeah.
Then what are you gaining here then? Are it just like if you're blocking on I/O in any of the Python, in any of these Python plugins that another branch would take, like another Go branch architect or wanted to just take over? Because that seems like a really big limitation that why have Go routines if you're only running like one at a time, really?
Oh yeah, no. The point is the entire agent is concurrent. This is just a piece. So the agent collects the metrics, aggregates the metrics, exposes an API, forwards the metrics to the backend. So we use Go routine all over the place. But instead of having a dedicated piece of software that works slightly differently because it has to run Python, the good thing is that it's seamlessly integrated. We still use Go routines, even if, of course, performance-wise, it's useless. Okay, thanks.